Hi to everybody. My name is Cesar. We'll talk about some preliminary topics necessary to understand quantum mechanics. And let's first point out some subjects are prerequisites for somebody who wants to work mathematically in a more sophisticated way in quantum mechanics. So, if you want to understand quantum mechanics, it is desirable that you know a little bit about, or maybe a lot, about complex functions, complex numbers, and all that stuff. You need to know uh, calculus, which means derivatives, integrals, and of course, linear algebra, matrices, vectors, and all that. You need to know that. These are the fundamentals for understanding quantum mechanics. Uh, Considering matrices an important subject, you need to know it is a fundamental object in quantum mechanics because you need to represent physical observables like energy and electric fields or position, momentum as operators, and these operators are represented by matrices. You need to know the fundamental operations, uh, addition, multiplication, determinant, trace, and mainly eigenvalues and eigenvectors. These are fundamentals to understand quantum mechanics. Okay, so I'll not go further into details of matrix algebra. You need to know about the multiplication, you need to know about the commutativity or perhaps the non-commutativity of matrix multiplication, how to calculate eigenvalues and eigenvectors, and how to deal with uh, matrices with complex numbers in its components, in its entries. But these are the main mathematical objects you need to understand. Okay, so we'll talk about one or two, maybe two concepts which are very important in understanding physics. Uh, this topic I will call particles and fields. You need to understand what is a particle and what is a field to understand properly physics, and in particular the quantum mechanical aspects of the nature of nature's description by physics, by quantum physics. So let us start about a definition of particles. We need to to contrast these two objects, these mathematical objects. So let us start by defining particles. What is a particle? We have an intuition about what is a particle. This piece of chalk here, it is what we understand as a particle. It has a finite extent. It has a definite position in space, and it has a dynamical evolution. If I let it at rest here at first, if I let it fall, it will fall through the action of the gravitational field. Maybe a particle is charged, so if you apply an electric field, it will move, being forced by the electrical forces or electromagnetic forces and so on. So particles are localized objects whose dynamics are parameterized by one important, perhaps the single parameter, which is time, time t. Okay, so particle, it is localized. It has a set of coordinates, position and velocity, and maybe internal degrees of freedom like spin or another properties, perhaps. And as time evolves, the particle produces the particle is subjected to some trajectory. So it has at each instant of time, since it is being localized, it has a finite, it's important to define particles, finite number of degrees, so-called degrees of freedom. Degrees of freedom, I can say in brief that it is, or they are, the number of parameters or coordinates which I need to specify at a given instant of time. This way, a particle, suppose a particle in Newtonian mechanics, will be specified by its position at a given time t and its momentum at a given time t. If it's a non-relativistic massive particle, momentum will be the mass multiplied by the time derivative of the position. But they must be understood as independent functions of a single independent variable, which is time. So particles are described, dynamics of particles is described by ordinary differential equations having time as the independent parameter. So if it's a non-relativistic particle, for instance, as a simple example, we'll have the derivative of the position with respect to time It is equal to the momentum divided by mass, which is the velocity of the particle, and the derivative of momentum with respect to time, it is the resulting force acting on the particle. So you see, dynamics of particles is described by a set of ordinary differential equations, time derivatives involved. These forces may be functions of position and momentum eventually, but since position and momentum are a priori functions of time, this force is a function of time. Okay, I'm assuming the system is completely deterministic, but this force eventually would be given by some randomized process, Brownian motion, and all that. But doesn't matter. You need to understand that a particle is a localized object in space which moves according to some dynamical laws, and those dynamical laws are differential equations relating time derivatives of the degrees of freedom. This way, if you consider a set of coordinates x, y, and z, okay, a particle, suppose in 3 dimensions, no spin, for the sake of simplicity, will be described by the set of coordinates position, momentum, and it will move along some trajectory, some path, and instant at a given instant of time, it will be described by the position vector r of t, this vector, which is the position vector respective to some origin of a given coordinate system, and the tangent vector to the trajectory will be multiplied by the mass, will be the velocity multiplied by mass, will be the momentum of that particle. Okay, so at any given instant, you'll have position and tangent to the trajectory momentum. And eventually it has an internal spin or something like that. Okay? So a particle must be understood as a localized entity described by a finite number of degrees of freedom. You have 6 here, x, y, and z, px, py, and pz, 3 coordinates for the position and 3 coordinates for the momentum. And you can have another set for spin, for instance, but it needs to be finite. The number of degrees of freedom is finite for a particle. Okay, so you can think about the initial condition, the starting point. What numbers do you need to specify a particle at time t equals to 0? You need the position. For instance, here I have a piece of chalk at 1.5 meters from ground, and it has a 0 velocity. So I have all the coordinates x, y, and z relative to some coordinate system, and vx, vy, and vz, or px, py, and pz, since I know the mass of this object. Okay, and electrical charge and all that. It can possess electrical charge. It can possess mass. It can have particular characteristics. Okay, so this is the definition of a particle. Okay, at time t equals to 0, I need the coordinates, the initial coordinates. Well, so to make things not much longer, let's talk about the other important aspect in physics, which are fields. What is a field? Well, as we know, a field is a dual concept of a particle, a dual in the sense, since a particle is a localized object, a field is, is an extended object over space which evolves with time, t. So it must be described by a function, not only in the variable time t, but also in the variables of space. So described by some function psi of r, the position vector, and time t. It is in sharp contrast to what we know is a particle. A particle, you have r is a function of t. For a field, r is independent of time. They are both parameters, okay? Parameterized by r and t, okay? A set of coordinates, x, y, and z, if you are dealing with a three-dimensional space, or in a single dimension, x and time t. Eventually, a field can be static or independent of time. Eventually, just like as an example, the electrostatic fields, a given temperature distribution, if it's not changing with time. But generally, fields change with time. Okay? So, if you need to have as arguments, as parameters to describe a field, not only time but position, it must be described by a set, eventually a single, but generally a set of partial differential equations. So, fields, partial differential equations. That's what you need to describe a field. In contrast to a particle, for which you need ordinary differential equations evolving with time only. Here, you will need partial differential equations whose differential operator as, say, L here, the differential operator. It can be a matrix eventually. It will depend on the time derivative, first order, second order, and I don't know how many orders do you need. And spatial derivatives, nabla squared, the Laplacian, or maybe higher order derivatives. So this operator operates over the field depending on position and time, and you'll get eventually a source which acts as the force, the forcing field. It is called a source. So S of position and time is source. Okay. As examples of fields, you can have the electrostatic, potential, electric potential. It is described by an equation depending only on position, which is equal to minus the charge distribution over the dielectric permittivity of medium. Okay, this is a static field. It doesn't evolve with time. This kind of field. I can give another example. Heat transfer, heat diffusion. It is described by the diffusion equation. It is described by an equation such like, suppose you have a temperature field. Temperature is position and time dependent, and it's equal to a coefficient which is called the diffusion coefficient, the Laplacian here of the temperature plus a source of heat eventually. This is a notice that a diffusion equation is first order in time, second order in space. And also we have wave equation. In electromagnetism, I'll have something like this. Now I have second order in space, second order in time. Suppose electric field here could be the magnetic field, or it could be a sound wave. So replace electric field by a scalar psi, and you have a sound wave here being described by such an equation, the wave equation. You have Maxwell's equations, which are a previous step in finding the wave equation for electric field in vacuum, for instance. Okay, so another example would be Maxwell's equations. They describe the electromagnetic phenomena, electromagnetic fields. So it's in the name, electromagnetic fields, because they depend on space and time. Okay, it's just to understand a little bit more. A particle is here. You have a set of numbers, the position and the velocity. It is here. You can see it. Of course, it's microscopic. You could have a very small, a really point-like particle which has a zero volume. But even in that case, you need only a set of numbers, the position, the coordinates, x, y, and z, and the velocity, the initial velocity to describe, and the dynamics will be driven by a time derivative equations. Only time derivatives appear. For a field, by contrast, say temperature. The temperature in this room is not localized here or there or in another point. The temperature is a field because I must say, by contrast to a particle, the particle is here. This is the position of the particle. This is the velocity zero of this particle here. For a field, temperature, for instance, I must say at this point in space, the temperature is like 6 degrees or 10 degrees or 20 degrees Celsius. In another point, I must assign another value of the temperature. So temperature is an extended object. At each point, I must assign a value for the temperature. And temperature, in this case, is a scalar field because just a number is needed to specify temperature at each point of space. And of course, temperature evolves with time. For instance, in the morning, early in the morning, it is normally it is usually colder than at midday. So it evolves with time and evolves with space. Eventually, inside a house, it is hotter than outside. So it depends at each point. The value of temperature depends at each point of space and at, at depends on the instant of time. Okay, so temperature is a field. Of course, there are vector fields such as the electromagnetic field. For specification of an electric field, I must say at this point the vector points upwards, and in another point vector points in another direction eventually. It has another magnitude and points towards another direction. Okay, so fields can be scalar fields, vector fields, or tensor fields, and so on. This is a scalar, temperature is a scalar, this is a vector field. Gravitational waves are described by a second or a rank 2 tensor. It's better to say that way. So fields can be scalars, vectors, and it doesn't matter. But the main important issue here is that fields must be parameterized by space and time. In contrast to particles, which are the coordinates are parameterized by time. Okay. Um, what else can I say? It's important make a comparison. Suppose I have a particle in one dimension, one spatial dimension. Let us call it x. Okay. So if I have a particle. Oh, I was I was forgetting to say a field. And let's just put it here. Field infinite degrees of freedom. That's an important issue about fields. For a particle at time t equals to 0, I need to specify x, y, and z, vx, vy, and vz, or position and velocity at the initial instant of time. But for a field at the time t equals to 0, I must specify a function. The value of the field at this point, the other point, and another point, and the neighboring point, and points in the line, there are infinitely many because you have a continuum. So if you need to specify at t equals to 0 a function, the values of the function at each point amounts to amounts to an infinite number of things I must specify. So infinite degrees of freedom. For a particle, you specify the vector, the position vector at time t equals to 0, the momentum at time t equals to 0. So in 3 dimensions, I will have 3 coordinates for position, 3 values for momentum. I will have 6 numbers here. And eventually you will have the number of spatial dimensions, so 2D, plus internal degrees. But if you don't have internal degrees, you need twice as many the number of dimensions, because you need to the position and momentum. So in 3 dimensions, for a single particle, you need 6 numbers, okay? For a field, by contrast, if you have a scalar field, which is the simpler one, you'll need psi 0 of r, which is the function evaluated at time t equals to 0. And they function in space. Suppose just a single space dimension, see psi of x as a function of x, you need to specify a function. A function for each value of x, assume a value. So you need an infinite number, an infinite uh, an infinite set of degrees of freedom, which are the values of the function at each point. Well, you can ask, so in practice, I'm not able to measure an infinite number of points for temperature, for instance. I cannot really measure temperature here and in the neighborhood of this point, separated by an infinitesimal, because my instruments are have a resolution, a spatial resolution. But we believe, to use a field theory, we believe in a property, which is a field is smooth. So I don't need really in practice to measure all the points. I need to measure a point here and a point in the neighborhood, assuming that if these 2 points are not so distant, not so apart, I can assume I can linearize or interpolate here what is happening. So I measure here, I discretize what I measure. I measure here, I can make a sampling effect. I measure here, here, and I know I can connect the dots because I assume the vector doesn't change too much here. It is smooth. It's a smooth function. Okay, that is very important. But let's make a comparison of a particle with field. So particle here, a single dimension x for a particle, space dimension for a particle. I will have x of t and p of t. So I can represent the motion as a function of time. A particle starts, suppose here, this is the initial position, it falls in an erratic manner, perhaps. And it goes here, it kicks on the ground, goes up, and I don't know. But this is the trajectory of the particle in the graph x of t versus time t. I need an initial position, and I will have another graph, which is the momentum. And suppose it has 0 velocity at time t equals to 0, and it grows and it reverse velocity in, I don't know, but I have a graph p as a function of time. Okay, That's what I need to know. And I can perform a phase space graph. It's called the phase space, usually. I can plot x of t as a function of p. Both are parameterized by the time t, so the particle makes a trajectory here, and this trajectory is the trajectory in so-called phase space. Okay, but notice at if I am looking at the line, this particle, suppose this is x, and its motion is confined to a single space dimension. What I see here is the particle starting here, it falls, it falls till here, and then it goes up again and stops here. Suppose somebody catch it here, it stops here. So the particle started here. What I see is a line. It started here, fall down here, kick here, and go up again, and stop at this point. This is the trajectory which I see in the line, the X line. Okay. Well, but what for a field in a single dimension field? I'll have a psi of x and t. So if I need to plot this function, perhaps I need to some knowledge about the derivatives of this field as a starting initial condition, say. But at time t equals to 0, I will have this thing here, a function psi 0 of x. And if I let time move forward, move in the future direction, this function evolves and goes, I don't know, maybe decaying over time if it's temperature. So this is time t equals to 0, time 1 unit of time, 2 units, and so on. And if I need to plot psi of x and t, I can put time t here, I can put the x-axis here, and what I'll have is the initial function here, some time interval has passed, so the function will produce a surface. Okay. Now contrast to the case of a particle. A particle, I have a trajectory over space as time passes. For a field, it's like an infinite set of particles moving, and this produces a surface. But remember, we are dealing with just only one space coordinate and time. And this field is assumed to be real, not a vector, a scalar, for instance. If I have a vector, okay, for a particle, you'll have y of t and z of t also. But for a vector field, I will have psi x of as a function of x and t, psi y, and all that for a vector field. And also, if I put just one more coordinate, spatial coordinate, y, for instance, I don't have the tools for produce a graph in which I have 4 distinct axes. So what I can do is slice over some of the variables. For instance, I can plot c of x and t for y equals to 0. And I can produce another graph for another y and another graph and so on. So I will have an infinite set of graphs. Perhaps it is enough to have 3 or 4 or 10 graphs. And if I add more coordinates, more special coordinates, what I can have is maybe a movie or something like that. The field is evolving in space as time passes. Okay, so a field is an extended object, and it's not localized here. So in a sense, there is a duality. A particle is a thing that's very well localized. A field is a thing that is extended over space. Well, there are fields which are wave-like. So wavelike fields, if you consider, suppose X here again, a field which, given the initial instant of time, it has this form, this distribution, and time passes, this field moves rigidly to another position. The peak is here, and now the peak is here at an x sub 0 here equals to the velocity of propagation multiplied by the time interval t, you'll have a wave. So waves are fields which in one dimension, one space dimension, has this form of dependence. It is a wave moving forward in space. As time passes in the future direction, the field moves in the positive direction of the x-axis, and this other function g is corresponding to a counter-propagating wave. It moves in the negative sense of the x-axis. The propagating wave and the counter-propagating wave. So a wave is a function it is a field which has a specific behavior. It is a function with, with arguments mixing space and time in this manner. X minus vt, x plus vt. Move forward, move backwards in the x-axis. If you have more coordinates, then you'll have a function of x, y, and z. Perhaps it moves only in the x direction, doesn't do anything in y and z. And if the wave is uniform and constant in the y and z plane and moves along the x direction, you call that a plane wave. Okay, that's the situation if you go from one dimension to 3 space dimensions. Okay, so wave-like fields must have a behavior such like that. That's a wave-like field. Okay, that's very important to notice. Another function, an arbitrary function, it's not necessarily, it can vary over time, but it's not necessarily a wave. So a wave is a field which intuitively we know propagates, it moves, the perturbation moves. So this perturbation moves forward in my figure here, my example here, my picture here, but it can move backwards. This move forwards, backwards. Okay, that's wave-like field. So if I am considering a monochromatic wave it has a single angular frequency, and it must be written as psi of x and t equals to an amplitude A for the wave moving forwards minus I omega t minus kx, the usual form, plus an amplitude B for the wave moving backwards, exponential of I minus I omega t plus kx. I am using the convention of physics. In electrical engineering, in many textbooks in electrical engineering, they prefer to replace the minus here by a plus sign in the imaginary unit, but it doesn't matter because in for real fields such as electric fields and all that, what really matters is the real part. But in quantum mechanics, wave functions are complex, are really complex numbers. You need to use, in fact, not just a mathematical tool, but they are they. It's a mystery. We don't know why in quantum mechanics the complex numbers are so important, and this is the convention: the time minus I omega t. So this is the forward moving wave, and this is the backward moving wave. Moves in the negative sense of x, and eventually you need to specify a k of omega. Okay, omega is a function of the k. The wave number is a function of the angular frequency, and this function, when you find for a specific wave what is the behavior of this k with the omega, you find what is called the dispersion relation. Okay, for photons, photons, the vacuum, you'll find that k is equal to omega divided by the speed of light in vacuum. That's the relation. So there is a linear relation. So you have something like this, k and omega, and this is just linear relation. Okay, but electrons, as we'll see, non-relativistic electrons with velocity much less than the speed of light, will have a quadratic relation. It's equal to k squared over 2m in appropriate uh, physical units. So it's the mass of the electron, and this is the as a matter of fact, you can plug in the Planck's constant here. So it's like this thing. So omega is a function of k squared. So you can plot. Okay, I can I can make it the other way. I can put k here and omega here. It's just linear again, and I can put k here and omega here. K is wave number, omega is energy. So I'll have a parabola. It's a parabolic dispersion relation for electrons, for non-relativistic particles. For relativistic particles, usually you have a linear dispersion relation, and for non-relativistic, you have a parabolic dispersion. That's in advance. That's an important behavior. Another another thing I want to call for your attention is this form of solution, minus I omega t minus k multiplying x, the exponential of this argument. You'll have here an amplitude, a complex. It is complex, a complex number, but is independent on x and t. It does not depend on space-time. Okay? And here you have a phase phi of x and t, which is equal to omega t minus k multiplying x. And this phase, if you choose a constant phase, suppose you want to move with the wave, and for an observer having a specific velocity, he will not see a change in the phase. It is called the phase velocity, but he can choose a phase. He can always be at phi 0 equals to 0 or equals to pi or equals to 1, or you can choose the number. It is omega t minus k multiplying x, and if you specify the x, isolate x in this equation, you'll have omega t over k. Notice it is related to a velocity of phase motion. It is a phase velocity because to obtain meters here and time is seconds, you need to multiply it by a velocity. So dimensional analysis show you omega over k is a velocity minus phi 0 over k. So you can isolate the x. And this x equals to some value, some distance in three-dimensional space. In space having three dimensions, it is just a plane. So this solution here is called a plane wave. Okay? A plane wave, it means at a given plane, x equals to, suppose phi 0 equals to 0, time t equals to 0, you have x equals to 0. X equals to 0 means the yz plane, x equals to 0, the yz plane. At the yz plane, you'll have a function whose value is a over the entire plane. In a subsequent plane, you'll have the same value but with a distinct phase. Okay, just the phase changes. But for x equals to 0 at the time t equals to 0, at the initial time, okay, suppose it's initial time t equals to 0, if you choose the phase equals to 0, it defines a plane. A plane equals x equals to 0. So you'll have the same amplitude over the entire plane. So this is uniform. Uniform because this doesn't depend on x and t, and it is a plane wave because if you ask the question, what is the surface of constant phase? If you choose a constant phase, what surface emerge from that? Plane. Planes are the surface of constant phase, and in those planes, the amplitude is uniform. Okay, so uniform plane wave. You can have distinct waves. For instance, if you replace x by r equals square root of the sum of squares, this thing here, you'll have a spherical wave, because radius equals to a constant will produce in 3 dimensions a sphere. So a sphere, in a sphere, you'll have a constant phase that represents spherical waves. But these form are uniform plane waves. It's a very important solution. Of course, you can generalize to 3 dimensions, and the equation of plane is just not the x, but some n, which is a unit vector perpendicular to the plane. It corresponds to the propagation direction of the wave, dot position vector. If you replace x by n scalar r, here you'll have a general solution for uniform plane waves. But a number multiplied by a direction corresponds to a wave vector. So you can have, for a general plane wave, this psi of r and t is equal to a e to the minus I omega t minus vector k, the wave vector, multiplying position vector. This is a general form of a uniform plane wave. Okay, let me finish here. I will just give you a taste of quantum mechanics in, in, in this video. We are finishing here, but a classical particle is described by some r of t, p of t. And if I go to quantum mechanics, if I go to the quantum world, a quantum, it is called the first quantization. A classical particle must be described by some probability density, and probability density is related to some complex field psi of r and t. Is the probability density of finding the particle in the neighborhood of r at the time instant t. And this is a field. This field must satisfy Schrödinger's equation and all that, but it is a quantum description of a particle, but it is a classical field. Okay? And a classical field, such as electric field, suppose, it is a vector function of position and time. But what it is in the quantum world? What represents what describes at the quantum level a field, a quantum field? What is a quantum field? Okay, so when you quantize a theory of a particle, a classical particle, you are doing a first quantization, and this leads to a classical field. If you want to quantize that field, a field quantization leads to a quantum field. And this is usually called the second quantization. Okay? So, for now, that's it. Thank you.